Hello dear students. In this video, in this lecture, we will discuss on the contraction mapping and fixed point theorem. So let's start with what is mean by the contraction mapping. Actually, contraction mapping, word itself shows that decreases. That is, whatever we have the points, then the distance between their images will be the less than their points in the domain. So the definition of the contraction mapping is that definition of contraction mapping. Definition of contraction mapping. Let xd let xd be a metric space. Let xd be a metric space. Let f from x to x be a function. Let f from x to x be a function. F is said to be a contraction mapping. F is said to be a contraction. F is said to be a contraction mapping. F is said to be a contraction mapping if there exists a real number. If there exists a real number lies between 0 and 1 such that distance between f of x f of y is less than alpha times distance between x and y. Distance between f of x and f of y is less than distance between x and y. So if we analyze this, this is true for all x, y. If we analyze this, what we get? Distance between f of x and f of y divided by distance between x and y is less than alpha and alpha is less than 1. That is, distance between f of x and f of y is less than distance between x and y. That is, the distance between images will be less than distance between their point values. That's why we say that f is a contraction mapping. It will be the contract the distances between the points. So this is an definition of contraction mapping. Now some examples of the contraction mapping. Let f from 0, 1 by 4 to 0, 1 by 4 defined by f of x is equal to x square with respect to usual metric is a contraction mapping. F defined from x to x, f defined from 0, 1 by 4 to 0, 1 by 4 closed interval by the mapping f of x is equal to x square with respect to usual metric is a contraction mapping. That is, we have to prove that there exists the real number alpha such that this condition get satisfies, such that this condition will be satisfies. Okay, let x comma y belongs to the interval 0 to 1 by 4, then d of f of x comma f of y is equal to mod of f of x minus f of y, usual metric. But f of x is what? X square minus f of x is x square and f of y is y square, which is equal to mod of x minus y into mod of x plus y, which is less than or equal to mod of x minus y mod of x plus mod of y, because mod of a plus b is less than or equal to mod a plus mod b, which is less than or equal. Now what is the maximum value of mod x? It is 1 by 4. Maximum value of mod y is 1 by 4, and adding this we get 1 by 2 into mod of x minus y, mod of x minus y, that is which is less than or equal to 1 by 2 d of x comma y. Thus f is a contraction mapping. Thus f is a contraction mapping. Next example. Let capital X is equal to L2 space. What is the L2 space? The space of sequences xn with summation of modulus of xn square is finite. Now define f from x to x by f of x is equal to x by 2, that is f of xn is equal to xn upon 2, and prove that f is contraction mapping. Then prove that f is contraction mapping. Consider the element of capital X is nothing but the sequence xn, and y is equal to the sequence yn. Both are belongs to L2. Now d of x comma y is equal to d of xn comma yn, which is equal to square root of the metric which are defined mod of xn minus yn square, mod of xn minus yn and square root of summation of xn minus yn square, and d of f of x comma f of y is equal to d of f of xn comma f of yn. Now the distance is defined like the function is defined by f of x is equal to x by 2, so d of xn upon 2 comma yn upon 2, which is equal to square root of summation of xn upon 2 minus yn upon 2 its square, that is which is equal to or which is less than or equal to square root of 1 by 4 summation of xn minus yn bracket square, which is less than or equal to 1 by 2 d of xn yn. Hence f is a contraction mapping, hence which shows that f is a contraction mapping with alpha is equal to 1 by 2. F is a contraction mapping with alpha is equal to 1 by 2. Now continuing this, we have a theorem that gives the relation between the contraction mapping and uniform continuity. Let XD be a metric space and F from X to X be a contraction mapping, then F is uniformly continuous. Now given that F is a contraction mapping, so to prove that F is uniformly continuous. Now in order to prove F is uniformly continuous, we have to given epsilon, then we have to find the delta such that the definition will be satisfied. So let epsilon greater than 0 be given. Also F is contraction mapping. Also F is contraction mapping. This implies there exists alpha lies between 0 and 1 such that d of f of x comma f of y less than or equal to alpha into d of x comma y for all x comma y. Now choose delta is equal to epsilon upon alpha, then d of x comma y is less than delta implies that d of f of x comma f of y is less than or equal to alpha times d of x comma y, which is less than alpha times delta, which is less than alpha into delta is equal to what? Epsilon upon alpha, so which is less than epsilon. So by choosing delta is equal to epsilon upon alpha, we can say that f is uniformly continuous. We can say that f is uniformly continuous. Now we have the definition of fixed point. Let XD be a metric space. Let XD be a metric space and F from X to X be a function. A point P belongs to capital X is called as the fixed point of the function f if f of p is equal to p. XD be a metric space and f is the function defined from x to x, then p belongs to x is called fixed point of f if f of p is equal to p. Now we have some examples of the fixed point mapping. So first example, let f defined from R to R by f of x is equal to 4 by 5x plus 5. That is, we have to show that p belongs to x such that f of p is equal to p. What is f of p? 4 upon 5p plus 5. That is 5 is equal to p minus 4 upon 5p. That is 5 is equal to 5p minus 4p divided by 5. So that implies that p is equal to 25. P is equal to 25. So 25 is the fixed point for this linear mapping. P is equal to 4 is the P is equal to 25 is the fixed point for given mapping. Next example, f defined from R2 to R2, f defined from R to R by f of x is equal to under root x square plus 1. Here we can say that f defined from R plus to R plus. Now let P belongs to R plus is fixed point of f. Then f of p is equal to p. So under root p square plus 1 is equal to p. This implies that p square plus 1 is equal to p square. So this implies that 0 is equal to 1, which implies that f of x does not have any fixed point. F of x does not have any fixed point. So these are the some examples and definition of fixed point. So in this lecture we had discussed about contraction mapping, some examples, some theorems, definition of fixed point and their examples. In the next lecture we will see fixed point theorem and some results related to the fixed point theorem.